All right, well, good afternoon to everyone who is there in person in Paris. I'm sorry I couldn't be there. And good morning to those who are watching online from North America. As I think most of you know, I'm Brian Stuart. I'm on the faculty at Drexel University, and I've been involved with the Plan 9 community now for a number of years. I got to thinking about it and realized it's been about 30 years since I ordered the CD and manuals that make up the second edition Plan 9 distribution. Though from software perspective I am mostly a systems guy, my research over the last several years has been primarily focused on the history of computing, particularly the ENIAC. Now, the ENIAC is a machine that was built at the University of Pennsylvania during World War II, and it was built literally just a few blocks from my office. So between that and proximity to the archives at the university, I've been able to take quite a deep dive into this machine, and it's been quite a fascinating journey. Part of this work has resulted in a simulator of the machine. Now, the simulator in its core is written in Go. That makes it portable, obviously, to a wide variety of environments. Depending on what environment it's in, different modes of visualization can be applicable. What I'm going to talk about today is some interfacing, visualization, and control interfacing that works on a Raspberry Pi under Plan 9. Now, the control box itself that we're going to talk about, well, this is a device that they could carry around the room with them. Now, the machine itself was literally a room. The space in which the operators could work was 32 feet by 16 feet, or roughly 10 meters by 5 meters. It was needless to say, a fairly large machine, and so if I wanted to go and clear something, initiate something, single step, it wouldn't be very effective to run across the room for it. So they had this portable control box with a cable long enough that you could carry it around the room, and it duplicated functionality that was on the main control panels of the machine. Now, the box itself, I have not found an engineering drawing of the original box. What I have found is one photograph, and from that photograph and doing a fair amount of pixel counting, I've put together this 3D printed model that I believe is quite close to the original, but I can't be certain, though I will point out that there was one bit of a brain fart in designing it. The cable on the real one comes out the bottom, not the top. Now, on this box, the toggle switch here has 3 positions that can be used to control different clocking modes that I'll talk about in a moment. And then these 4 buttons are push buttons, momentary contact push buttons, that are used for initiating certain operations within the machine. Now, the clocking controls give us these 3 options: a continuous mode, a 1 add time mode, and a 1 pulse mode. The clocking of the machine is based on a master 100 kilohertz clock. That clock is divided into segments of 20 pulses, and each group of 20 pulses constitutes 1 addition time. This is the basic operation of the machine, somewhat analogous to executing an instruction on current machines. The continuous mode lets the clock free run. It's the way you would normally use it for doing calculations. If I set the switch in the 1 add mode, then I can use one of the push buttons to single step the machine 1 addition time per push. So it's effectively like single instruction execution. If I set it in the 1 pulse mode, then the pressing of the button is 1 of the 100 kilohertz pulses. So you can watch the execution of an operation step by step through its progression. The 4 push buttons, the first one is the clear button. Now this sends a signal to all of the accumulators to reset them back to 0, and it also resets any other counters that are involved back to 0. The reader start and initial pulse buttons are used to initiate a computation. Now, which one is being used depends a little bit on the design of a particular computation. Some computations begin by reading a card from the input and then processing the data on that card. Others begin with computation rather than reading input, and so the initial pulse switch handles those. The 1 pulse 1 add button is the single step button. In the 1 add mode, pressing it does one group of 20 of the 100 kilohertz clock signals, and in the 1 pulse mode it does one of them. Now the station itself is connected in terms of our simulation to the Raspberry Pi pretty much in the way you would expect, i.e. GPIO lines. And the Plan 9 interface to these GPIO lines is in the form of a read operation. Here we're reading, and in doing that read, you get all of the GPIO lines in one read. I should point out this is the version that is distributed on the 9legacy.org site. The 64-bit value that comes in is represented as 16 hex digits. So we're going to read a 16-digit value, convert it to a 64-bit integer, and then use bitwise ANDs to look at the state of the specific GPIO lines that are connected to each of the individual switches. Once we recognize from the pattern an operation that needs to be performed, then what we do is we essentially pass a string, which would be the same as the string that a user might type at the command line interface to carry out the same function. For example, the clear button. For debouncing purposes, we do the reads every 10 milliseconds, and then we don't operate on a given measure or reading until we see 4 in a row that are all the same. So when we see 4 in a row that match, we now look at it, compare it to the previous stable reading that we had, and now we ask, does this represent a change that needs to be sent as a command? The code for doing this basically looks like this. We have our 10 millisecond wait, we read the 16 bytes, we turn that into an integer, and then mask off and look at the bits to figure out what to do. Now, I'm only showing an excerpt here. The only one of the commands that I'm showing at this point is the one that recognizes the pressing of the clear button. So that call to proc command B space C is sending the B space C command, as one might type at the keyboard, to the command handler. So that's the control station part of it. In a lot of ways, for this particular bit of work that I'm talking about, the more interesting part is the display. In specifically an LED array. Now, I'm using here an off-the-shelf matrix that is 16 rows by 64 columns. The way it's made is out of a group of 8 by 8 monolithic LED modules. These modules are then soldered into a board that has circuitry on it to present an interface to this 16 by 64 grid. The way the interface is structured is there's a 64-bit shift register. That represents then one row of LEDs. The shift register chips involved also have a latch on them. So you can have a stable output while you're shifting in a new group of 64. You pulse the latch signal, and then it copies the values from the shift registers into the latches. Those latches then are connected to one side of each LED within a row. So a given position of the shift register will be connected to all of the LEDs in a column. To select which of the rows we're looking at, we have a 4-bit decoder. The particular board I'm using, this is implemented actually as two 3-bit decoders with a 4th bit selecting which of the two decoders is active. But the effect is we have 4 input lines and 16 that represent the output of the unique states of the 4 bits. There's an enable line also that's gating that row selection, which then connects to the other side of each LED. So in effect then, by selecting a row and setting a bit in a column, you are turning on or off a given LED. The effect of this obviously then is that we need to multiplex the display by showing one row at a time and cycling through that. And if we cycle through it fast enough, then we will have what appears to be a stable display. This is something we're pretty familiar with. Now, the basic algorithm that we're going to go through is this. We're going to transmit our 64 bits over the SPI interface. It turns out that the characteristics of the shift register chips in terms of polarity and phase of the clock matches mode 0 of SPI, which also happens to be the default mode on the Raspberry Pi when you bring it up. So that's going to be how we send a row of LED values. 64 bits then, of course, is 8 bytes, so we'll be sending a group of 8 bytes, loading up the shift register. Then we're going to turn off the enable. So while we were shifting it in, we had one row of LEDs that we're displaying. We're going to turn that row off, latch the new 64 values in, set up the address, and then turn the enable back on. And finally, deassert the latch. The deassertion of the latch can be done, in any number of places. It just kind of makes the most sense to do it while you're leaving the LEDs on. Now, the code for doing this looks essentially like this. There have been a few different variations on how this is done, but this is the basic model. The first line there is the writing of the 8 bytes to the SPI interface. And then the sequence of prints there doing various set operations on the GPIO lines is carrying out that sequence of pulsing the latch, turning off and on the enable, and setting up the address lines. And then, of course, we finally increment our row number. We have a sleep 1 here, which I'll say just a little bit more about in a moment. Now, there are several different ways you could structure this. Perhaps the most natural way that most of us would think of is, I'm going to periodically refresh the whole display. The thing about that in this scenario is you end up with a very quick refreshing of the display, and then you turn around and wait a period of time with nothing turned on before you refresh it again. The effect of that, well, it amortizes the work across that, but it unfortunately leaves the LEDs off most of the time. Now, the effect of that is relatively dim illumination, which from a purely realistic simulation perspective isn't really all that bad, because the neon lamps in the original machine weren't particularly bright. But for the purposes of having something for exhibiting and showing people and explaining how the machine works, it'd be nice to have those things a bit brighter. So the next approach is, okay, let's do it where once a millisecond, I update one row, leave it on for the millisecond before I update the next row. And that's essentially the code that you saw before. Now, if we do that as an ordinary time-shared process, this has a little bit of an issue that comes up, particularly when the simulator itself is running, because the simulator is quite compute heavy. There are a very, very large number of channel messages being sent, and that eats up some amount of CPU time. And so you end up with a display that has a tendency to kind of flicker and blink, and it's not a good, solid, steady display, unlike the real ENIAC, where the neon lamps would be quite solid. So the next step in development was to say, okay, let's use the real-time scheduling mechanism of Plan 9. In this case, what's going to happen is that sleep that we have here at the bottom, it'll become a sleep 0, which effectively means yield. And then what we'll do is we'll configure the scheduler to say, schedule this thing once a millisecond. And the way we do that is this. When we create the process, we're going to open its control file, and then we're going to send a sequence of messages. The way you do this in Plan 9 for a real-time process is you first write messages that configure the parameters of the real-time scheduling. In this case, we're setting the period and the cost both to 1 millisecond. And then you send the message admit. When you send the admit command, it goes through and checks the parameters that you've set and says, does this set make sense for a useful real-time process? If it does, the write succeeds and the process is put into the scheduler. If, on the other hand, the set of parameters do not make sense, then the write fails. So even though I'm not showing it in this slide, in the real code, I've got a test on the fprint printing the admit message to see whether it succeeds or not, to make sure that I have configured the real-time scheduler in a way that will actually function correctly. Now, it turns out that the real-time scheduler works generally quite well, but not perfectly. If there's nothing else going on the machine, scheduling it once a millisecond is generally quite reliable, and you get a good solid image. And I should mention, by the way, that the rate at which we're updating is somewhat critical. My original thought had been, if I can update the screen 30 times a second, that should be good enough. After all, movie film classically was 24 frames a second. NTSC television, each half of the interlacing was a 60th of a second, so the full frame was done every 30th of a second. However, those environments are ones where there's enough persistence that it turns out that you can kind of get away with a little bit slower than you can with these LEDs. It becomes very noticeable that there is a blinking effect going on at 30 frames a second. So 60 frames a second is pretty much necessary here. So this means then that the 1 millisecond per line is a fairly important number. But if the system is heavily loaded, even with the real-time scheduling, you can still sometimes see some flickering. I'll say a little bit more about that later. But for that reason, the next experiment was to write a kind of minimal device driver in the kernel. And this device driver really doesn't do much more than hook into the basic timer and say, wake me up every 100 milliseconds. And then it does the update of one row. So the code for that looks something like this. Now the bottom part of it is essentially the same as what we had before. That is, these calls to GPIO out are carrying out the same operation as those fprints were doing the set operations. The top half of this is essentially just the write to the SPI port. Now, this turns out to be slightly more involved. In the code itself, there is, when you do a write to the SPI device, a call to a function that initiates a SPI operation and then unblocks the process when the SPI operation is complete. But I can't use that here. The reason is that it uses the DMA controller and waits for an interrupt when the DMA controller is finished. But because this is tied into the timer, this is itself running in an interrupt handler. And so once you're in an interrupt handler, you can't block waiting on an interrupt. So this is actually recoding the guts of the SPI interface to do polling. The polling is kind of interesting here as well. It turns out that in order to know when the next byte you can write is, there's a bit that tells you it's ready to take another byte. But that bit's not the same bit that tells you it's done writing all the bits. And so what happens is, when we're writing 8 bytes, we look for the one bit 7 times, and then after we've sent the 8th byte, we look for the other bit. And that's why that loop is structured the way it is. So it's a little bit weird, and you'll notice that we've got these 2 while loops that are going to just spin waiting on the bits to tell us it's time. You might be concerned, at least I was concerned initially, that this might take a bite out of the system's CPU time. It turns out it really doesn't turn out as bad as I had feared. In looking at the statistics reported by the kernel, I find that it actually is only it's only increasing the amount of time spent in interrupt handlers by about 1%. So, you know, if it was already at 1 percentage point, this bumps it up to 2 or something like that. So it turns out to not be nearly as problematic as I was afraid it might be. And as a result, then, it actually does function pretty well. Now, what I'm going to do next is I'm going to kind of show you the whole thing in a demonstration mode. Before I do anything else, though, I'm going to mute the audio so that it doesn't create nasty noises as I move the camera. Okay, so this is the 1/8 scale 3D printed model of the ENIAC. Up here is where the LED display is located, and then there are 3D printed baffles in front of it to allow through only those LEDs that we're actually using. So I'm going to start by running the real-time priority version of it. For time, I'm not going to run all of the different versions. Now, this one is, as I said, running the real-time scheduled version. So it actually looks fairly good in this presentation, partly because of the responsiveness of the camera, and partly because as the display is being moved, it's less obvious when there's flicker going on. To give you a little idea what's going on in terms of the operation here, I'm going to go ahead and shift it to the one add mode here. And now I'm going to carry out some operations. Actually, this is the one pulse mode. So if I do it to the one add mode, you can see it doing various steps. And there it is back at full speed. Now, even though it's not very easy to see here, as I said, there is a certain amount of flickering that does occur even with the real-time scheduling. So what I'm going to do now is switch it over to the, I'm going to have to reset this keyboard. I believe it's a power supply issue that sometimes this keyboard will basically die on me. Okay, now I'm going to restart it running with the kernel driver. And there it is running with the kernel driver. Again, unfortunately, because of the nature of the camera, the frame rate, all this sort of thing, I'm not able to really show the difference very well. But it's still an interesting one that I want to investigate further. So let me go ahead and stop this and get back to the presentation. So this, as I said, it was kind of an interesting thing that came up, trying to understand why the real-time handling didn't necessarily give us a good way of dealing with millisecond level resolution. I have a conjecture about this. I don't know for sure what it is. I haven't really had time to dig into it yet. My suspicion is this. When a real-time process is released, it gets put onto the ready list as you would expect. It appears at the highest priority on the ready list. But I don't think that it immediately preempts a running real-time time-shared process. So because time slices are several milliseconds, that means that a real-time process might have to wait a few milliseconds before it can actually do its thing. And for something that's meant to run every millisecond, it's possible that this is causing a delay that's enough to create this flicker. I don't know for sure that that's what's happening, but that's my suspicion. I do have a student who has indicated an interest in doing a research-oriented senior project. And so we're looking at possibly digging into this more deeply. A couple of things immediately come to mind that we would want to look at. One would be to, first of all, look at the way the scheduler is designed and verify this question of, does it in fact preempt immediately? And if not, what would be involved with actually doing that? An alternative that definitely seems like kind of an interesting one, especially now that we're in a world where virtually everything is multi-core. What if we reserved one core for the real-time processes and the interrupt handler? Let the other cores, in this particular Pi that I'm running, that's 3 other cores, let those be used for all the time sharing processes, and then have the one core reserved for the real-time activities. Don't know yet how well that would work, and I don't know how much surgery is going to be required on the kernel to do it, but I think it's going to be an interesting avenue of study. So that's where I plan to go with this, and I'll be glad to answer questions that anyone has. Thank you.
So, should there be any questions, please come up here. and take this beautiful microphone, and we get the camera here, so you get a picture as well. Just send here. Symbolically, that would be where somebody asks a question. Does anyone have a question, actually?
Don't worry, my feelings won't be hurt if nobody has a question.
Yeah, we're getting there. It was coming. Thank you so much for volunteering.
Yeah, the reaction in the room was to ask you to coordinate with Ron and his team with Nix, because you can get like a core for your process can have his own core and do its stuff without being bothered by the kernel or whatever. And
Yes,
also, I don't know. Yep, sorry, go on.
yeah, I definitely think that's a direction that I want to look at is looking to see if the Knicks work would make sense here.
Sleeping for a constant amount of time is not a very good idea. Maybe you could like see how much time you have left and sleep only that amount of time, and, like a game loop.
Right. And that, in fact, does make sense. And I do it in some other stuff that I've done. The only issue here is that I would have to go to a different form of the sleep mechanism because the sleep call is in units of milliseconds. And I would have to then go down into a sub-millisecond kind of resolution for that part of it. But yes, I did think about doing that. It's just that I would need a different form of sleep.
Also for the flickering, if you do that, I think you can skip frames. Like if you are late, you don't have to do all the frames, and maybe that could stop the flickering. Even if you are interrupted by the kernel, like you can drop the last 3 frames and go on with your life. And I don't think it will be noticeable by the naked eye, just looking at the LEDs.
Yeah, in fact, the updates that are happening inside of the simulation are faster than we're updating the screen anyway.
Yeah, I had I think a similar question. Like the hardware is so cheap, and these microcontrollers are so cheap now that it seems like you could not worry about like shift register or do the shift register thing, but that's actually just giving uh, the the data to some microcontroller that's gonna keep track of the display until you're ready to tell it, okay, go to address a different location.
Certainly, that could be done. I'm kind of treating the Pi as dual purpose in this regard, being the microcontroller for that and also running the simulation. But you're right, I could very easily connect a lower performance device like a Pi Pico or something and have it control things.
Uh,
All right.
do you have original ENIAC programs, or do you have to write your own?
Well, that's an interesting question. Um, there is a very small amount of recorded ENIAC programming out there. It seems that they didn't do a lot of keeping and hanging on to their programming. Uh, there's a lot of references to, oh, we did this, but nowhere do you actually see the exact configuration of the machine that they did that with. There have been a couple of papers written, in fact, that have attempted to reconstruct ones. There's one that I and some students are working on right now that we have a fairly complete diagram of the wiring of the machine for the problem. But what we don't know is, was this the kind of initial version of it before they started trying to do any debugging? Was this the final version of it? And in later papers that were written about it, there have been mentions of a couple of different kinds of bugs, and we don't know for sure if they were ever resolved. So the reality is there's a lot of open questions with respect to that.
We got one more question coming up.
Sorry. And can you tell us a bit more about the program you showed us running? Because I was under the impression like one row should only have one light because it's 10 lights and it's a digit. So why do we have a line full of light? And you see what I mean?
Okay. Yes. So let me first of all kind of characterize what the array of lights is actually saying. Each of the units that we saw, there were 4 in this model. Each of those is an accumulator on the machine. Now, each accumulator can store 10 digits. Now, the position of the illumination vertically is telling you the value of the digit from 0 to 9. And then horizontally, you're looking at the 10 different digits. So at any point in time, you should see exactly 1 illuminated LED in a column, but then there will be a total of 10 across the line. There's actually 1 extra pair all the way over to the left. That is the sign of the number. So that's what you're looking at. The particular programming that was running in the little demonstration was just a simple number theoretic problem that was searching for all of the 3-digit numbers that are equal to the sum of the cubes of the digits. And you were seeing 4 of the accumulators that were involved in that. There's actually a total of, I think it's, if I remember right, 14 accumulators being used in that problem. Or 11, I forget.
All right, we got one more question coming up for you.
Okay.
Hello, I have a question about the history of computers and evolution of, the evolution of computers.
Mm-hmm.
So, if I look back at a lot of the old papers I read, clearly they, you were talking about scheduling and cores, dedicating a core to real-time workloads. What are, let's see, how do I formulate this? In your view, what things have changed a lot from hardware and software perspective? But really, the software hasn't changed. The software hasn't adapted as much as it should have. Perhaps it's we should take a different approach to scheduling or memory management or IPC or other things. But in practice, we're stuck in the past. So what things would that be?
I think you really kind of hit the nail on the head at the beginning with that. It really, I think the biggest difference is in the amount of parallelism we have now. We spent pretty much the first 70 years of the field living in a world where if you had more than one CPU running concurrently, it was an unusual situation. And we spent a lot of time in the 80s looking at what are the different ways we can interconnect these CPUs. Nowadays, we're kind of living in a world where we've got a substantial number of CPUs. Even on a tiny little Raspberry Pi, we might have 4 cores, all sharing the same memory space. And I don't think we've done a lot of thinking about what is the best way to utilize that kind of functionality. The ironic part of this is that the ENIAC was originally a very parallel machine. Each of those accumulators could be doing something simultaneously with all of the others, and there were a total of 20 accumulators on the machine. There's a mathematician by the name of Derek Lemer who had done some really interesting stuff on the machine doing prime number work. He actually created a sieve to generate prime numbers, and it worked in parallel. So it basically tested divisors in one step. And in a later conference, he made the comment that the ENIAC was a wonderfully parallel machine until von Neumann spoiled it. But the funny thing is that there are also comments by, like, Press Eckert, he was the main engineer on the machine, where he later said, okay, we're going to focus just on things that are serial because programmers find it so difficult to understand and manage the parallelism. So it's been a very interesting evolution in that regard. And I feel like we're still kind of in the early days of understanding what's the best way to think about and use the fact that the reality is going to be parallelism is going to be to our advantage.
Thank you.
Right, so that's it for this talk. Thank you again very much. And I hope we can find somebody to get you this beautiful trophy here.
Yes, I would appreciate that. We can figure out a mailing address, either that or sometime we'll find a way to do this.
Yeah. All right. Yeah. Thank you very much again.
Thank you.